Hi all. We can define a translation operation as the translation from one point to another point having similar surroundings. The vector which we use is translation vector t equal to u1a1 plus u2a2 plus u3 a3, where u1, u2, u3 are arbitrary integers and a1, a2, a3 are our primitive translation vectors. Okay, so we can define our primitive translation vectors such that we should be able to write our translation vectors in this form. Okay, two lattice points are connected by a translation vector in this form. Okay, any two lattice points are connected by a translation vector in this form. Okay, now we're going to define primitive cell. A primitive cell can be defined as the parallelepiped defined by primitive axis a1, a2 and a3. This a1, a2, a3 are our primitive translation vectors. So the parallelepiped defined by the primitive axis a1, a2, a3 are called primitive cell. This is our primitive cell. This is the fundamental building block of the crystal. The repetition of this fundamental building block, the repetition of the primitive cell make the whole crystal. Okay, so this is known as our unit cell. Okay, a primitive cell is type of cell or unit cell. And another point is a cell will fill all space by the repetition of suitable crystal translation operations. Okay, in two dimension, let me define this is one lattice point, and I am defining one translation vector, primitive translation vector a1, and here it's a2. Okay, I'm making a translation operation by using a translation vector t equal to 0 a1 plus a2. Okay, 0 a1 plus a2 means 0 a1 plus a2 is this point. And another translation operation, I am doing another translation operation by using the translation vector a1 plus 0 a2, a1 plus 0 a2. Okay, that is this point a1. The translation vector is a1, that is this point. Then another one I am making t equal to a1 plus a2, a1 plus a2. So this is a1 plus a2. So another translation vector I am making. This is another lattice point. Then t equal to 2a1 plus 0 a2, and the t equal to 0 a1 plus 2 a2 Okay, so the first one is 2a1, the second one is 2a2, the second one is 2a2. So I got two lattice points here. In the similar way, I can make infinite number of lattice points by using this translation vector. Okay, so that is the third point, tells us a cell will fill all space by the repetition of suitable crystal translation operation. Okay, simply we can show in 2 dimension. The similar thing happens in 3 dimension too. Okay. So the next point is a primitive cell is a minimum volume cell for a given lattice. Okay, no cell having less volume than this primitive cell can make the crystal by its repetition. Okay, only by repetition of the fundamental building block, only by repetition of the primitive cell we can make the whole crystal. And the last point is, and the next point is, the number of atoms in a primitive cell. The number of atoms in a primitive cell is known as primitive basis, is always same for a given crystal structure. Okay. So the next point is the volume of a parallelepiped with the axis a1, a2, a3 is V equal to a1 dot a2 cross a3. This is the volume of the parallelepiped, and here our primitive cell is a parallelepiped, and the volume of the primitive unit cell is V equal to a1 dot a2 cross a3 by elementary vector analysis. The last point is there is always one lattice point for primitive cell. Okay, let me consider a parallelogram as primitive cell, and each lattice point shared among 4 primitive cells. Okay, so each corner of a primitive cell contain 1 by 4th of the lattice. Okay, 1 by 4th portion of the lattice. Each corner of one primitive cell, or each corner of each primitive cell contains 1 by 4th of the 1 by 4th portion of the lattice. Okay, so the total lattice, total number of lattice inside a primitive cell equal to 1. So that is the point. There is always one lattice point per primitive cell. Okay, when we are considering, when we consider a lattice point in the 3-dimension, let me consider this point. Let me consider this lattice point. This lattice point is shared with 8 primitive cells. Okay, this lattice point is shared with 8 primitive cells. Okay, one is this one, second is this one, and third this one, fourth this one, and fifth this one, sixth this one, 7 and 8. So that means each lattice point shared among 8 primitive cells. So 1 by 8 portion of a lattice point is there inside one primitive cell. Okay, one corner of the primitive cell. So 1 by 8 into total 8 corners are there. So total number of lattice points inside a primitive cell is 1. Okay. There are many ways of choosing the primitive axis and primitive cell. Okay. These 3 figures, these 3 parallelograms, like parallelogram 1, 2 and 3 are equal in their areas. Okay, in this way we can select, in this way we can select, and this way we can select a primitive cell in the given lattice. Okay, look at this. This is a primitive translation vector A1 and A2. Primitive translation vectors A1 and A2. If I want to select this point, so the importance of translation vectors: 2 lattice points are connected by the translation vector T. Okay, any 2 lattice points can be connected by the translation vector T. Okay, so if I select this point, then the translation vector I can select in this way. This is minus A1 plus A2. Then this is the translation vector T. Okay, T equal to minus A1 plus A2. In this way I can connect this point. If I select this point, then this is the translation vector. That translation vector I can make with, this is minus A2, that is T equal to minus A2 minus A1. Okay, so by using this primitive translation vectors, integral combinations of this primitive translation vectors, I can make a translation vector. I can connect it to lattice points. Okay, and the same way, if I select this point, okay, this is lattice point, then I can write the translation vector. I can write the translation vector T as, by using this primitive axis A1 and A2. Translation vector T as minus 2 A dash plus A2 dash. Okay, minus 2 A dash plus A2 dash, minus 2 A1 dash. Minus 2 A1 dash is this one. Okay, that is minus 2 A1 dash plus A2 dash plus A2 dash will give this translation vector. Okay, plus A2 dash will give this translation vector. Okay, in that way I can select any point by using this 3 primitive unit cell as well as this primitive translation vector. Okay, in the fourth figure, fourth parallelogram, if I want to connect with these two lattice points with the translation operator t, then I need to write t equal to a t equal to a1 sorry, this is a1 triple dash. Okay, this is a1 triple dash. This is a1 triple dash. So I can select t equal to a2 triple dash plus half of a1 triple dash. Half of a1 triple dash. This is half of a1 triple dash. So this is not integral combination of a1 triple dash and a2 triple dash. So in this, by using this primitive translation vectors, I cannot connect two lattice points with a translation vector. Okay, so in this figure, this parallelogram, I cannot choose as the primitive cell, and this translation vectors a1 triple dash and a2 triple dash, I cannot choose as primitive translation vector. Okay. Let us discuss another way of choosing primitive cell. Is known as Wigner-Seitz shell. By the following procedure, we can construct a Wigner-Seitz shell. Draw lines from the given lattice point to all nearby lattice points. Okay. So these green lines are the lines which is connecting the given lattice point with all other nearby lattice points. Okay. At the midpoint, and normal to these lines, you have to draw new lines. And this two lattice points, when you are considering these two lattice points, this is the line normal to this green line, and at the midpoint. And when we are considering these two lattice points, this is the line at the midpoint. And when we are considering this lattice point, this is the line at the midpoint. Okay. The smallest area enclosed in this way is known as Wigner-Seitz shell in 2 dimension. Okay, in 2 dimension, the smallest area enclosed in this way is Wigner-Seitz shell. Here I got a hexagon. Okay. In 3 dimension, in the similar way, you have to connect all the nearby lattice points with this given lattice, and you have to cut the midpoint of that lines with here its lines, and in 3 dimension you have to cut the midpoint with the planes. And the smallest volume enclosed in that way is known as Wigner-Seitz shell in 3 dimension. Okay, here we got a hexagon, and as the condition of primitive cell, only one lattice point is there inside this hexagon, inside this primitive cell, or this primitive cell contain only one lattice point. Okay, the repetition of this hexagon here in the 2 dimension, in this given array of lattice, the repetition of this hexagon make the whole crystal. Repetition of this hexagon make whole crystal. Okay, like this. Repetition of this hexagon make the whole crystal, like flooring with hexagon tiles. Okay.